Hello, I'm Noah Holkbor. I'm an undergraduate at Grand Valley State University, and today I want to talk through some of the strengths and limitations of using photography to study tree architecture, specifically looking at a destructive conformation and a pilot study involving 4 species. A little bit of background first. The woody parts of any tree have 2 main tasks. They got to transport water and they got to provide structural support. And trees are constrained by biomechanical and physical factors, and so these tasks can be studied using various mathematical models. We use Murray's law, which predicts area preservation at a branching point and is an estimate for hydraulic efficiency. We use the West-Brown-Imquist model, which is about mass allocation and the total mass that can be supported after a branching point. And the uniform stress model, which is about the support of the limbs, and it takes branch angle into account. And quickly over at the right, you can see that's just a branching point where we have labeled the mother and the daughters, which is used in all of these models. So why a non-destructive method? All previously published research, it's been done destructively, and which limits the potential avenues of study. A non-destructive method would allow for longitudinal studies, large-scale studies that would be impractical destructively, and would just make the field and this type of study more accessible and potentially cost-effective. And so our destructive conformation, simply its goal was just to determine if measurements from photos could even offer a valid alternative to destructive measurements. We took an Acer rubrum. It was 33.5 centimeters in DBH and 23.4 meters tall. It was cut down at each of its branching points, we call nodes. Following the leading path were photographed, and we took measurements physically, like directly from the nodes, and from scaled photographs using ImageJ. Now the photos that we used, they were taken in the lab from cut node sections, as an example on the right there. It's not what we initially planned. It was due to a miscommunication. The original plan was to have photos taken before the tree was cut down, and while it's unfortunate that that didn't actually happen, these type of photos still offer us an interesting opportunity in that they show ideal conditions. It'll controls for photo resolution, light, perspective distortion, and so it'll still offer kind of this valid baseline for what is possible with photos. Jumping into our results, we found a significant correlation between the direct and photo measurements. Looking at the figure on the left, we've got the direct mothers on the x-axis and the the photo mothers on the y-axis. In our correlation there, we had an R-squared of 0.988 and a p-value of less than 0.001. So there's clearly a correlation here between them, which makes sense for measuring the same thing. However, when we look over at that figure on the right, we do see that those triangles, which are the photos, are consistently overestimating the direct measurements in those larger nodes, and it diminishes as they get smaller. And even though that happens, and we don't really know why it is, we still think that photos offer a useful form of data, especially because the models are not necessarily based on the gross measurements, they're based on the relative measurements of the mothers and the daughters. But moving on to the pilot study, whose goal was simply to assess if photos generate sufficiently accurate data to distinguish between species for a given task, and inside of one species between tasks. And there on the right are just some example photos of ginkgos from the study. We took scaled photographs of the first node, first branching point for 4 species, and example photos are there on the right. We used Ficus grandifolia, Quercus rubra, Acer sacrum, and Ginkgo biloba, and 30 trees for each species. We measured their DBH and took photographs. And all these trees were located in West Michigan parks, forests, and in the case of ginkgo, in the city streets of Grand Rapids. And then in ImageJ, we measured the characteristics of node 1. There on the right, you can see the mother labeled down at the bottom of that branching point, and the 2 daughters and that angle. That's what we measured in ImageJ. And then the mother-daughter ratios and the branch angles were used to quantify branch geometry using our models, or using the models we've chosen. And now we're here with the results of Ficus grandifolia. I want to first draw your attention to that figure on the left, talking about Murray's law. On the x-axis, we have the Murray's mothers, and on the y-axis, we have Murray's daughters, and all the figures are going to be kind of set up like that. And then we have our blue line and circles, which are observed, and the red triangles and the red line, which is our predicted. And those predicted values were actually calculated by taking the residuals from the observed regression and applying them to the predicted. And the predicted is just allometry, the predicted is just isometry. And so it would be too easy to find significance if we just compared the observed with that. And so we kind of did that to have a fair test. And I also want to point out that in that left figure, in the table in there, we show the data for the predicted regression, and we don't show that data for other figures, and that's just because the predicted regression, it's isometry, it's always going to have a y-intercept of 0 or practically 0, and the slope's always going to be 1, and so we omitted it from other tables just to be space efficient. But actually getting to the results for Fagus grandifolia, in this case all three models show negative allometry. They show a significant difference from isometry, or from the predicted, and they have an increasing safety margin, an increasing deviation associated with increasing node size. And I'll interpret that for each of these models. Looking first at the left again with Murray's law, we see that as the nodes get larger, that deviation from the predicted also gets larger, and that means that in the larger nodes they're going to be less hydraulically efficient, but that also means that they're going to be less likely to experience an embolism, and that's why it's called a safety margin. Because if you're optimized for the task, you also might open yourself up to some risk. Looking at the center, that's for the Westbrown-Enquist, talking about total mass. And again, as you get larger, the nodes get less optimized, so they're going to be supporting less mass than they theoretically could. And then on the right, looking at the USM, talking about the supportive branches. As the nodes get bigger, they become less optimized, so their branches might be less massive or at a less risky angle. And so there's some sacrifices there, but it also means that those larger nodes are going to be less likely to buckle or break under their own weight or under the stresses caused by wind or snow. Briefly, I want to focus in on Quercus rubra, and I say briefly because, again, all three models show negative allometry with an increasing safety margin associated with increasing node size. This is the exact same story as with Fagus grandifolia. Murray's law, again, larger nodes, less hydraulically efficient, less likely to experience embolism. Westbrown-Enquist in the center, larger nodes, they are going to be supporting less mass than they theoretically could. On the right, USM, larger nodes, they're going to be less optimized for their limbs being large, but they're going to be less likely to break off under stress. And I really want to hammer home that the real kicker when it comes to Quercus rubra is that it's the same story as Fagus grandifolia because those two are closely related species. And here they have similar branch architecture, which is, I think, biologically what we would expect. And that, I think, lends some credence to this type of methodology and study, in that here we have two closely related species behaving similarly. Moving on to Acer sacrum, we see the exact opposite story. All models show isometry for Acer sacrum. This indicates optimization and less of a safety margin. So for Murray's law on the left, that means that throughout the tree it's going to be optimized for hydraulic efficiency, but sugar maple might be opening itself up to more risk of embolism. In the center, Westbrown-Enquist, sugar maple is going to be more consistently supporting the amount of mass that it theoretically could after a branching point. And with the USM, those branches, they might be more likely to break off due to wind or snow, but they are they're gaining other benefits in terms of their mass and maybe their kind of structure. But what's really important about Acer sacrum in the terms of our study is that this right here demonstrates that data derived from photos can distinguish between species. If Acer sacrum's results are distinct from the previous two that I just talked about, and so that shows that it's not that photos are always telling the same story. Here they are distinguishing between species. And before I move on to ginkgo, I want to have a quick aside, and I want to talk about the optimization of node 1 of Acer sacrum, what I just went through, and its similarity to the destructive Acer rubrum, the nodes 1 through 30. If you look at that table on the right, we can see that we have this kind of two scenarios and three models. And it's almost isometry across the board, except for the Westbrown-Enquist for the Acer rubrum. And even though our ANCOVA picked up a significant difference there, or a marginally significant difference, the deviation from allometry, when you actually look at the figure, which is the one on the left, is pretty slight, and so we should interpret it cautiously. Looking at that figure, I mean, the ANCOVA found a significant difference, but it's pretty dang close to isometry. And you can compare that to the center figure, which is for the 30 Acer, the Westbrown-Enquist. And so across the board, they're pretty similar. And I think that this suggests that for Acer, node 1 might not just be a good gauge of what's happening at node 1, but the overall functional architecture of the tree, because here we have similarities between Acer at node 1 for 30 individuals and for one individual from 1 all the way up to 30. It's the same story, which I think is consistent with what we would expect. Now, those are the kind of figures and data, if you want to really dig into that for what I just talked about. But I want to move on to ginkgo biloba. Ginkgo biloba had a mix of results, and that lends evidence to the ability of photo-derived data to not just distinguish between species, but inside of one species to distinguish between the models. And there's a couple caveats to that. One, I want to note that for the Murray's Law and Westbound Inquest, the two models for ginkgo that showed negative allometry, they were marginally significant. But we think that in this case, marginal significance is still compelling, as photos are going to increase the likelihood of type 2 error, especially at the larger nodes, and so marginal significance is still indicating that there's seemingly something going on other than pure isometry. And it's also worth noting that it's possible that a negative allometry could emerge for the USM, which we found isometry for in this case, if at larger nodes, but maybe our methods and the size distribution didn't capture it. We didn't get a whole lot of large ginkgos in our sample. So this certainly is not a definitive last word on ginkgo biloba. However, at this point, it seems to point that photographic data can not just distinguish between species, but between models within a single species. And to wrap this up in summary, I first want to bring us back to the destructive conformation and just re-emphasize that photos can approximate direct measurements. We had a strong correlation there. And although there's this overestimation that occurs in larger nodes that we still don't really know where it comes from, and we're hopefully going to be able to account for it at some point, there's still a valid comparison to be made there, and we still certainly think that photos are valid, especially because the models that we use aren't based off of the gross measurements in centimeters. They're based on the ratio between the mothers and daughters. And so even if there's an overestimation, if the ratio is still correct, it should still work in the model. And to bring us into the data I just talked about, looking at this table on the right, we can see that data from photos show species-specific trends. We see Fagus grandifolia and Quercus rubra optimizing similarly, and they're related. But they optimize distinctly from Acer sacrum and ginkgo biloba. And this is all consistent with what we would biologically expect. And so, taken as a whole, this all seems to support the conclusion that a photographic method could certainly play a valuable role in future study. It's not going to completely replace destructive study, and it shouldn't. Destructive study offers valuable insights in how precise and accurate that the data gained from it can be, but it has a lot of limitations. And photographic methods do too, but I think that they can both serve their own purpose. I think photographic methodologies might have a niche in future studies, especially studies that are going to require a large amount of data that would be prohibitively challenging to do destructively, or that are going to be a longitudinal study. Additionally, this could just open up pathways to easier access to this type of study. And before I wrap up, I want to look forward. We're constantly improving our methods, whether that's trying to get scale bars up in trees close to nodes, or work on photo camera stuff to minimize distortion. We have a plot study in the works right now where I took photos and data from over 150 individuals in a plot. There might be some interesting stuff there with crowding and neighbor effects, and also it gave us practice with some real-world stuff where we had to take pictures of trees that were in crowded forests. And we want to look at microanatomy to see if there's any sort of relationship between the microanatomy of the species and the architecture of it. This is the literature I cited earlier. Of course, it's just a selection from the vast literature that's out there on this topic. And of course, thanks. I want to thank Gary Greer for his excellent mentorship and for the teaching he has given me over the past 2 years of working with him. I want to thank Stephen Polowski for his work on the destructive conformation, and Brendan May, Nicole Foy, and all the other students involved in this project over the past years and who have been involved in Greer's lab. And I want to thank Grand Valley State University for funding through the listed grants. And of course, finally, I want to thank you for watching this presentation. Thank you so much for taking the time to hear what I have to say and for engaging at the conference. If you have any questions or suggestions or comments, I would love to hear them. You can use the system with the Botany conference or through email. My contact information is up there. Thank you so much for listening to my presentation. I hope that you enjoyed it, and I hope that you enjoy the rest of the conference and that you have a lovely rest of your day. Thanks again.